Alright, so in this video, what we're going to do is introduce the idea of L'Hopital's rule and just present a couple of examples to see how it's used in context. So, L'Hopital's rule states that if you have, let's say you're taking the limit as x approaches some number c of a function f of x divided by a function g of x, if this limit turns out to be, if it ends up, after trying to use direct substitution, ends up being 0 divided by 0, or positive or negative infinity divided by positive or negative infinity, we can say that it's also equal to the limit as x approaches c of the function's derivatives, so f prime of x and g prime of x. And this is a very powerful tool, because now, instead of having to rearrange algebraically, we can now use derivatives connected to a limit and find what x approaches. Alright, let's do some examples. Example number 1, it says to find the limit as x approaches 1 of 2e to the 2x minus 2 divided by x squared plus x. So first things first, say you see this on a test. First we need to make sure that direct substitution doesn't work. So if we tried direct substitution, we would get 2 times e to the 2 times 0, so I'm just going to put 0, minus 2 divided by 0 squared is just 0 plus 0. Alright, well, let's simplify the numerator a little bit. E to the 0 is 1, so 2 times 1 is 2, 2 minus 2, well, that's just 0. And we have this indeterminate form, so we've kind of hit a roadblock here. What we need to do is say, hey, I can actually apply L'Hopital's rule here. So I'll do just that. What we need to do is find the derivative of the numerator, and then divide that by the derivative of the denominator. So let's do that. We know that our new limit is going to be the limit as x approaches 0 of, this is going to involve a little bit of the chain rule, but let's just say 2 times, because it's just some constant outside of the, that we are going to differentiate, our scalar, if you will. So the derivative of e to the x is just e of the x. So the derivative of the outer function, which is e to the x like I had said earlier, with respect to the inner function, which in this case is 2x, times the derivative of the inner function. Our inner function is 2x, so we're going to multiply that by 2, minus, well, the derivative of 2, the derivative of a constant, is just 0. So I could write plus 0, but you get the gist. And then on the bottom we have here the derivative of x squared. Well, we're just going to use the power rule, so that's 2x. The derivative of x is 1. And now we have our new, well, actually I could simplify this a little bit. That will just be 4 times e to the 2x divided by 2x plus 1. And then from here, let's try plugging in 0 again. So that would be 4 times e to the 0, once again, divided by 2 times 0 is 0 plus 1 is 1. So we've actually made a bit of a development here. So we're almost done here. E to the 0 is 1, so that's 4 times 1 is just 4 divided by 1. We get that the limit as x approaches 0 of this function, or this function divided by another function, is 4. So 4 is our final answer. Alright, let's do another one. Example 2. Find the limit as x approaches 1 of 1 minus x squared divided by the natural log of x. So, once again, you should be in the habit of trying to use direct substitution if you can. So let's try that right here. So 1 minus, well, 1 squared is 1, divided by the natural log of 1. So, well, we know that 1 minus 1 is 0, and that the natural log of 1 is also 0. So once again we have this indeterminate form. So we say, hey, maybe right now is a good time to use L'Hopital's rule, and we will. So our new limit, as x approaches 1 in this case, is going to be, well, the derivative of 1 is 0, minus the derivative of x squared is 2x. And that's just me using the power rule. Now here's just one of those things that the natural log of x, its derivative, is 1 over x. Alright, let's simplify this a little bit. I can rewrite this as negative 2x over 1 times x over 1. And that's just a basic dividing fractions rule. So that's negative 2x squared divided by 1. So my new function that I can try out is negative 2x squared. So let's plug in 1 for x. So that's going to be 1 squared is 1 times negative 2. Well, that's just negative 2. So our limit as x approaches 1 of, the function we had just talked about is negative 2. Alright, so let's keep this going. Example 3. Now example 3 looks like there's a lot going on here. We're taking the limit, we have some cosines, a pi in there, and e. Right, so let's do what we'd normally do and just say, hey, let's see if direct substitution works. So wherever there is an x, we'll plug in a 1/2. So that's 1/2 times the cosine of, well, pi times half is just pi half. All divided by e to the 1/2 minus the square root of e. Now let's just see what we get from here. Well, the cosine of pi halves, or pi over 2, we know that's just 0 from our unit circle. So that's 0 times 1/2 is 0. Divided by, well, let's see here. We have e to the 1/2 minus the square root of e. What's important to just know right here is that one of my basic radical properties is that I can rewrite the square root of e, or really the square root of any number, as that number to the 1/2 power. So since that's true, well, we have e to the 1/2 minus e to the 1/2, that's just 0. Alright, so it's at this point that we can see L'Hopital's rule is going to be pretty useful. Now there's a couple things going on here, so we'll just take it a little bit slow. So to take the derivative of the numerator, let me get a new color. Let me write this in green. We're going to need to use the product rule, because you can see we have a function x times another function cosine pi times x. So, like I had said earlier, the product rule, well, that just says if we're multiplying two functions, we take the derivative of the first function times the second function plus the first function times the derivative of the second function. All of this with respect to x, of course. So, now that we got that just cleared up, let's see the derivative of the first function, and in this case I just want to make it clear that the first function is x. And then the second function you could think of as the cosine of pi times x. So, the derivative of the first function, the derivative of x, we just say that's 1, times the second function. We haven't done anything to the second function yet, so cosine pi x plus the first function. We talked about how that was just x. Alright, times the derivative of the second function. Now the second function right here, cosine pi x, it might not be immediately obvious, but what we have here is an application of the chain rule, because we have the function pi x inside of cosine x. So the chain rule says, well, to find this derivative, we need to take the derivative of the outer function, which in this case is cosine of pi x. So its derivative is negative sine, right? And then with respect to the inner function, pi x times the derivative of the inner function. So the derivative of pi x is just pi. So we have all this going on, divided by, well, the derivative of e to the x is just e to the x. And then, so minus the derivative of the square root of e. Now I just want you to remember the derivative of the square root of e is going to be 0 because we're taking the derivative of a constant. So I'm just going to write e to the x. So let's simplify this a little bit. This will be the cosine of pi x minus, let's write it as pi x sine of times sine of pi x, all divided by e to the x. Okay, so we're almost running out of room here, but let's just try and use direct substitution now. So that's going to be, let me see if I can get more room in here. So that's going to be the cosine of pi halves minus 1/2 times pi times the sine of pi halves divided by e to the 1/2. Alright, so we have a lot going on here, but cosine of pi halves we had said was 0, so I'm just gonna cross that out. We have here negative pi over 2 is what's left after we multiply these across. Negative pi 2, well, times sine of pi halves. Pi halves is just 1. So I'm just gonna leave it like that. And it's that, the negative pi halves divided by e to the 1/2. Okay, so once again we're gonna use that division rule that we had talked about earlier. Negative pi halves times its reciprocal, the reciprocal of the denominator. So 1 over e to the 1/2. And this almost concludes the problem. Negative pi halves, right? That's what we had beforehand. And now in the denominator, I'm also going to include the square root of e, or e to the 1/2. So that is our answer, right there. Okay, example 4. Now example 4 is an example of infinity limits. So I had said earlier that L'Hopital's rule works when it's plus or minus infinity divided by plus or minus infinity, right? And that looks awful. That's an awful infinity symbol, but you get the gist. When we're dividing infinity by infinity, well, we're not really sure what's happening there, so we need to use L'Hopital's rule. But just to give an intuitive sense, if we were to plug in infinity for each of these x's, just thinking about that, as x gets bigger, the natural log, when we take its natural log, it'll still get bigger, and then once we cube that, it's just getting bigger and bigger towards infinity. So we get infinity. Now on the bottom, same thing. If I were to multiply infinity by 4 of it, it's still infinity, and then if I were to take its natural log, it's still going to be infinity. So I'm kind of left in this weird situation where I still need to find this limit. So let's do just that. We're going to use L'Hopital's rule and a little bit of the chain rule, like I had said earlier. So this is the limit as x approaches infinity of, oh my bad, of, well, it changes a little bit. So now we're going to take the derivative of the outer function, and notice here that the derivative of the outer function is x cubed. Oh, my bad. Switch to pen. It's x cubed, because we have the natural log inside of that x. So the derivative of x cubed is 3x squared, but instead of x I'm going to write the natural log of x, because this is the chain rule. Now, times the derivative of the inner function. So the inner function is natural log of x, so the derivative would be 1 over x. Now all of that divided by, well, the derivative of the natural log of 4x. So once again, the derivative of the outer function in this case is 1 over x. With respect to the inner function, so 4x, times the derivative of the inner function, times 4. Alright, so let's simplify this, because it sure could use some simplifying. So that's 3 natural log of x, well, this whole thing squared, divided by x, divided by 4, divided by 4x. So we have two fractions essentially divided by each other. So what we're going to do is rewrite this as 3 natural log of x divided by x. Oh, my bad, this is squared, times, and we'll just take the reciprocal of the denominator. So that'll be 4x divided by 4. And actually, I can do some cancellation right here. I can cancel out the 4's. I can even cancel out the x's. So the final function that I can test out is 3 times the natural log of x squared. So, from that, we will try to plug in infinity. Well, what happens if we were to plug in infinity? Well, take the natural log of infinity, we'd still get infinity. Square whatever we get from there, we're going to get infinity. Times 3, we're also going to get infinity. So, do I say, hey, is the answer infinity? Let me try. Let me try to make that look a little bit nicer. Infinity. So, do I stop here, or what happens? Well, like, generally what you want to do is keep going and see, well, how far can I go with L'Hopital's rule? But what you'll notice is I can rewrite this as natural log of x squared, or where the square goes outside of the parentheses, divided by 1. The derivative of 1 is 0, because it's a constant. So I can't go any further, because then my new limit would be undefined. So my final answer is that, hey, yeah, the limit as x approaches infinity of the function we just talked about is infinity. And maybe that's not a very satisfying answer, but visually we could see, like, on a graph. Let me try making a graph on the left. We could say, well, as x is moving, say we had a function that was moving as x got bigger and bigger, y also got bigger and bigger, like that, infinitely. So, you know, that's kind of what's happening here. It's not reaching a point like an asymptote or anything like that. So, to conclude, the answer is infinity. Now, it's not always going to be infinity, because we didn't, it would seem like we just did all that for no work, and saying, oh, well, it was just infinity all along. There are cases where it's very common too, actually, for it to not be infinity. So let me pull up an example. 5x squared minus 8 divided by 7x minus 4x squared, and we're trying to take its limit as x approaches infinity. So, once again, we would try using direct substitution. 5x squared minus 8, well, if we were to set x equal to infinity, that's just infinity. And on the bottom, we have 7 times infinity minus 4 times infinity squared. That's negative infinity. And we get negative because this portion right here is growing much faster than this portion right here. And we're subtracting from that smaller portion. So, regardless, we're going to have to use L'Hopital's rule here. And taking its derivative won't necessarily be that difficult. The limit as x approaches infinity of, well, let's take the derivative of the numerator. So just using the power rule, that's 10x minus 8. The derivative of negative 8 or over 8 is just 0. So we would really be subtracting 0. So I'm just going to write 10x. And then on the bottom, the derivative of 7x is 7 minus, well, the derivative of 4x squared, that's 8x. And we're going to try it again. Hey, let's see what happens if I were to plug in infinity here. Well, we would just get infinity on in the numerator, because think of it as infinity times 10 is still going to be infinity. It's kind of hard to think about, but that's essentially what's happening here. And on the bottom, we'd get negative infinity again too, because 7 minus infinity, essentially, we're going into the negative infinities from there. Because we're subtracting infinity from a number that isn't infinite. So, let's see, can I go any further? I actually can. In this case, I actually can go further. In the last problem, I couldn't, but this one I can. So as x approaches infinity, so let's see here. The derivative of 10x is just 10. The derivative of 7 is 0, minus the derivative of negative 8x is negative 8. You're like, hey, what do I have here? Well, that's actually our answer. I can reduce that as 5 over 4, and that's negative 5 over 4. So after we actually had to use L'Hopital's rule twice, we can say that the limit as x approaches infinity of the function is negative 5 divided by 4.